6. He's famous, I guess, because of the very impressive books on operator algebra, Kadison books. Yes. What is Kadison duality? It's this duality between complete order unit spaces and convex compact Hausdorff spaces. So this morning Prakash talked about compact Hausdorff spaces, zero-dimensional compact Hausdorff spaces being equivalent to body and algebras. This is a more quantitative duality, so it's not obtained by homing into the two-element set, but actually into the real numbers, as I will explain. And it's a duality of a different nature. The essentials were published by Kadison already in '51 in a memoir of the American Mathematical Society. He published only one half of it, the representation of all the unit spaces. But I never looked it up, but I understand that Stone in his original publication also only did one half representation of body and algebras, and not a duality in this form as we would now describe them in categorical terms. It's an equivalence between categories. But definitely what Kadison proved was the difficult part of the duality. So together with my PhD student Robert Ferber over there, so he's someone very knowledgeable in this area, we discussed this a bit and we chose the name Kadison duality for this duality because it doesn't appear to have a name yet, so I think it's appropriate to call it after him. It's appropriate, I guess, at this meeting to talk about it because it's fundamental in quantum foundations, at least in the mathematical side of quantum foundation, because it precisely describes the duality between states and effects, as has come up already a few times in this meeting, and it gives a very, very precise mathematical description of it. Effects, predicates, or observables, I'll describe this a bit more precisely in a minute. And that's really one of these results that's crying out, I would say, for a precise categorical treatment. And that's what I will do here. So, what are my own contributions to this? Basically, very, very, very little. So there are no new mathematical results. I'll describe in a few minutes how I became interested in this. But at some stage, I decided for myself I'd like to understand this duality in greater detail. And I sat down to work out those details. And it took me a couple of weeks. And not continuously, but to find everything. The material is scattered around in the literature. There are many places where you can find bits and pieces. In many books on functional analysis, it's mentioned somewhere in the beginning, but then they say, oh, this is trivial, or they refer to some other source that only contains a small part of the whole story. So I set myself the goal to really work out this. And then the invitation came for this meeting, and I thought, well, it might be appropriate to talk about this here. It's really something that's nice to lecture. And it's not cutting-edge research, but it's very relevant, I think, for what's going on at this moment. So I will give a rather thorough presentation of it as far as is possible in such lectures. So I will have some proofs here and there, but I will not go through all proofs. That's simply impossible. But I'll clearly give the structure of the proofs. There is possibly some novelty. I mean, these order unit spaces are interesting vector spaces. I think they're also maybe not so well known, and I'll put them in perspective and I relate them to some other mathematical structures, and this gives rise to some interesting categorical structures. The main structures I will be talking about are sets, compact Hausdorff spaces, and convex compact Hausdorff spaces. I'll explain a bit more about that later. What what is the relevant literature? Of course, this is the original article by Kadison. It's not available on the web, at least I could not find it as a PDF. And this is a collection of sources I use to assemble a proof. You'll probably recognize some of the classical books in Kadison Ringrose, the Alfson, Asimov, Alice, some of the classical books in functional analysis, but I also made use of some research articles, some of them more recent and some of them a bit older. So it was really a matter of collecting things. What are prerequisites? What do I assume in these lectures? Well, basically linear algebra, basic topology, basic category theory. But what does basic category theory mean? I'm aware that not everyone here is very fluent in category theory. They'll use categories, functors, and junctions. And the main reason why I use them is for organizing material. Category theory is very good at doing this, putting structures in relation to each other. And even if you're not very familiar with category theory, I hope you will see the main lines there, how structures are related and how you can define translations back and forth between them. Okay, so what are the relevant categories I will be talking about? I'll define them later in more detail, although many of them have already appeared here. And it's also just a fixed notation. So sets, convex sets, CH I'll write as an abbreviation for the category of compact Hausdorff spaces and continuous maps. I'll write CCH for the category of convex compact Hausdorff spaces. Now it's already immediately a bit subtle how to define objects in this category. When I say CCH, I simply mean structures which are both compact Hausdorff and convex. In principle, there's no relation between the two. But there is a subcategory of so-called separable compact Hausdorff spaces where points can be separated, when different points in a space can be separated to, or it maps to the unit interval. So, so X is in CCH set. If I have two elements in this X, then there is a map from X to 0, 1, or for which phi X is not phi 1. So they are separated by a map to the unit interval. Now the unit interval is compact Hausdorff, and it's also convex. So it's inside this category. And this map should be both continuous and affine. And affine, I'll describe more later in more detail, means that the convex structure is reserved. Now, I find this separability condition most convenient to work with, but what you see more often in the literature is that these spaces are described as subsets, convex subspaces of a locally convex space. That's actually equivalent, but I find it a bit more awkward to work with. Other categories of interest, effect modules. The last few years I've been doing quite a bit of work on effect modules. I'll describe them briefly as a motivation for this work. They are mathematical structures that capture effects in quantum foundations. And, but I will not go into the details here in this talk. And the category of order unit spaces, and there is a subcategory BOUS, where B stands for Obama, or complete order unit spaces. Similarly for these effect modules. Okay, one of the reasons why I got interested in this, and this is still motivation and background, is that I at some stage stumbled upon this adjunction between effect modules and convex sets. So this is an adjunction, this is a way of translating these structures in both directions, and it's a very fundamental adjunction because it describes the duality between states and effects in the quantum world. as a category theorist, when you see such an adjunction, you're interested in restricting it to get an equivalence. This is work I did with a former PhD student, Jorgen Mandelmaker, and we came to an equivalence between Banach effect modules and these convex compact Hausdorff spaces with this separation condition. This was in QPL about 3 years ago. How we proved this was actually via Kadison duality. So what we proved was this equivalence between these effect modules and these order unit spaces, and what we simply appeal to then to get the equivalence between here, between the left hand side and the right hand side, we simply assume Kadison duality. So at some stage I thought, well, let's not just assume it and elaborate the details. There's an interesting broader picture to paint here in relation to especially C-star algebras. Because if you take a category of C-star algebras here at the bottom with positive unital maps, you take the opposite of this. This is the most natural form to consider C-star algebras. Then there are some relevant functors or operations. So there's on this side the states functor, and states of the C-star algebras, they are the positive unital maps to the complex numbers, and they carry the structure of convex set. They're also compact Hausdorff, and they satisfy the separation conditions, so you end up in here. If you take the self-adjoints, you get these order unit spaces. So the self-adjoints, they form a vector space over the real numbers, and they have some additional order structure and the norm and completeness in the norm, and that gives you precisely these complete order unit spaces. And the effects give you these effect modules. So in this picture, you can see see a split. On the one hand, you have these effect modules and these order unit spaces. They belong to the world of Heisenberg, where you look at transformations on predicates, on the observables. And in logical computer science terms, you would describe these as predicate transformers, like Prakash also mentioned. On the other hand, you have the state transformers, which belong to the world of Schrödinger. So this picture really captures some essential aspects of what's going on here from a computational perspective. And observables can be described either as self-adjoints or as effects, and people sometimes switch between these two approaches, and that's justified by the equivalence that you have here between those categories. Now, just briefly to mention what are effects. Effects of a C-star algebra are the elements, the positive elements below the identity. So you can describe them directly like this, and somewhat interestingly, you can also describe them as positive unital maps from C square to C-star algebra A. And is that clear to everyone, or shall I briefly describe how this works? But if you have a function like this, then I can define E to be f of 1, 0, which is an element of A. This is an effect. It's positive because, and I assume this map is positive in unit. The pair 1, 0 is positive, f preserves positivity, so this is a positive element. It's below 1 because if I do f of 1, 0 plus f of 0, 1, this is also a positive element. This is f of 1, 1, which is 1. Because f is unital, it preserves the unit. And so this E, if I is 1 if I add a positive element to it. So this E is in 0, 1, A. Conversely, given such an E, I can define a function C squared A by and it's easy to see that the two of them are in bijective correspondence. What I will be talking about this weekend at the Prakash Fest is a more logical approach to this. Now, the complex numbers are initial in the category of C-star algebras. So if I go to the opposite category, they are final there. I can describe them as a 1 there. And C squared, I can describe them as 1 plus 1. And so fx become maps to 1 plus 1. And this looks similar to predicates in ordinary set theory, which are, can be described as characteristic functions, also going to 1 plus 1. So there's a formal similarity here that I will be exploiting later on. Good. And states, by the way, are maps from A to the complex numbers, which in the opposite category, by the way, are maps from 1 to A and can be seen as points. Good. So the setup of the proof I will describe to you involves some categories, and this is the overall structure. So I'll have a category of vector spaces, normed vector spaces, Banach spaces, which are complete normed vector spaces. And you can also look at ordered vector spaces, and ordered unit spaces have both an order and it turns out also a norm. Banach order unit spaces have a complete norm, and then for these I have this equivalence. What I will do today is describe this left leg. And tomorrow I'll describe more of this leg. This left leg mainly contains basic results from linear algebra. So it's not very deep at all. Good. Any questions about this? Clear? So let's, yeah?
When you mentioned effect as going into 1 plus 1, could I think about this as the sum of two effects, one and it's orthogonal?
No, it's a single effect. And it's an interesting point because from this perspective, as we discussed yesterday, there's not a complete duality between states and effects. So states go from 1 to A, so they produce something in A, but effects do not go into 1. I guess, however, a subtle point, if you work in a category of C-star algebras with subunital maps, so f of 1 should be below 1, then effects can be identified with maps from A to complex number, from A to 1. But I don't know if that's what you're doing, but at least there are different perspectives on all this, depending very much on what kind of maps you use in the category of C-star algebras. Okay, other questions, remarks? Good. Prakash's lecture this morning was very helpful in setting up already this picture of dual equivalences. You have a category 1 in opposite form and functors between them, and typically this going from one category to another happens via such schizophrenic or dualizing object where you look at the maps going into this object. If you do this, set theoretically, there is a double dual map from x going to d to the power x, and ddx of f is simply function application like Prakash described. Set theoretically, this is already an injection, but in other situations that need not be the case. And typically what one does in these proofs of equivalence, one just restricts the maps here in a suitable way, but also the maps here. And this should then give a representation of x into these function spaces. And I'll describe two examples. Stone duality, what Prakash described this morning, sends a Boolean algebra into the continuous functions to 2 from the Boolean function from b to 2. And as was mentioned, you can describe these Boolean algebra maps to two as algebra filters and the continuous maps to two as closed subsets. So this gives you this description. But it's really, really obtained by restricting this this double dual map. Now the same thing happens here for Kadison duality. We'll take an order unit space, which is a certain vector space, V, and we will restrict the map from V to the real numbers by looking at the positive unital maps. Implicitly also they're required to be linear, and they form an convex Hausdorff spaces. So once you have that, you can look at the affine continuous maps from this space to the real numbers, and you can find V in there again. So this gives a representation of these order unit spaces. And an important theorem then is that this injection is an isomorphism if and only if V is complete as a space. And this is just the kind of result you expect in this work. And this map here is obtained as a restriction of the double dual map for a vector space going into this double dual. So my starting point today is look at this double dual map. So to define a bit more precisely, if I have a vector space V over a field K, where K is typically the reals or the complex numbers, in the beginning certainly that does not matter very much. I'll write V star for the dual, and this is sometimes called the algebraic dual, to distinguish it from other kinds of duals. In particular, it's good to mention that this double dual map, EE from V to V star, V double star, is linear, it's natural, as Bart said, it's an isomorphism if V is finite dimensional. Now if we have not just a vector space, but a vector space with the norm, of describe that in detail a bit, I can look at a different dual, which are called W sharp here, norm or bounded dual. They made the maps to this scalar, which are not only linear but also bounded. And both these spaces carry topology, the weak star topology, which I will describe later on, and I'm just giving an overview. And the main result today is that for an arbitrary vector space, there is a surjection here, like this, from V to the continuous dual of V star. And in the normed case, there's actually an isomorphism from the continuous dual for the norm dual. So it's very subtle here. You have these different dual spaces, which give you different restrictions on the original algebraic dual. And I will explain you about this in the remainder of the talk. So this is the overview. Any questions about this? Is it clear?
What happens if the dimension is finite? Do any of these linear natural the ISO fails?
Yes, that's true. Absolutely. Yeah.
And linear and natural?
No, that remains the same. That was also what Prakash mentioned. Because the naturality is not, it does not depend on a choice of basis. The isomorphism from V to V star, which exists in the finite dimensional case, on the basis of the fact that these spaces have the same dimension. Right? You get an isomorphism there by choosing a basis. If you choose a basis for V, that gives you a basis for V star, and you get an isomorphism. But the isomorphism depends on a choice of basis. To the double dual, you don't need to have a choice of basis. There is a map going into that. And if the space V is finite dimensional, you know that V star and V double star has the same dimension. So this map must be an isomorphism.
Yes.
Yeah.
Yes, I know, but I'm saying in the infinite case,
Yeah.
which of these adjectives fail to hold?
No? Yeah, only the
Just
iso.
ISO.
Only the iso. Yeah.
It's the same map, so still natural.
Oh, okay, fine.
Yeah. Just go through the calculations. That's,
Oh, no, I could go through this.
But now I don't believe it.
yeah, well, if you don't believe me. Any further questions? Yes?
I understand because even in the dimension is infinite,
So what are you saying? If the space is finite dimensional?
No, infinite dimension.
It could be.
Yeah.
Yeah, it can happen, but it's not in general.
Okay.
Yeah.
Because with the axiom of, with the axiom of choice, you can always choose a base, so you can prove that the double dual has the same dimension as the space, and you can always take this map, so you can prove that they are isomorphic.
Yeah, but in category theory, we don't like to have such things which depend on the choice. Right?
The choice only is to prove that there is an isomorphism.
That doesn't hold an infinite dimensional base. You can prove that there is a basis, but you can't prove that they're the same size.
Why does it want to be?
It would
Yeah,
be
oh,
larger.
sure. If you have the axiom choice, you know it should be larger.
Okay.
Thanks.
Attack team is ready.
So let's get to work. So first result, basic result in linear algebra. If I have a vector space, then omega, I'll typically write omega for these linear functionals in algebraic view. Omega is a linear combination of other such linear functionals, if and only if this intersection property of the kernels of these omega I is contained in the kernel of omega. This in one direction it's easy. So if omega is such a linear combination and something is in the kernel of all these omega i's, that means that it's mapped to 0 by all the omega i's, then it will also be mapped to 0 by omega. So one direction is easy. The other direction, you prove by induction on n, and the base case is interesting in itself. If I have two linear functions and the kernels, their kernels are included, then one is a scalar combination of the other. This in itself is already a slightly surprising result. The proof is not very difficult. Let's try to go through. If omega is a zero map, it's trivial. Right, so I'll rule this out. Now, if omega is not trivial, I form the kernel, and it's an injection into K. Now, K is the space of scalars, which is one-dimensional. So this quotient is also one-dimensional. So I can choose a base vector of it. And I can choose it in such a way that this space, this quotient space, is K times this base vector, with base vectors written here with this coset notation. Now I take K is rho B divided by omega B. Here I need to use that omega B is non-zero, but I'm assuming omega is non-zero. If omega B is 0, then the whole function is 0 because B is a base vector. Now I can use that the kernel of omega is contained in the kernel of rho, so rho factors from this quotient also as a function to K. And namely in this way, rho bar V plus this coset is simply rho V. That's well-defined function there because of this inclusion of kernels. Now, in order to get finally this equation, what you do, you pick an arbitrary vector, you write it as a scalar combination of this base vector, and then this is just writing out 3 or 4 or 5 equations that summarize the situation here, and it follows. So it's really basic linear algebraic reasoning, and I'll come back to this. I'll really need this result. So a linear functional is a linear combination of other things if and only if I have this kernel inclusion property. Good. If I have a vector space and a collection of linear functionals, I can define the topology on this. And this is a very general formulation for this. So if capital omega is a subset of these linear functionals, I get the so-called weak topology on V, and that's the weakest topology that makes each of these functionals in capital omega continuous. Now, this is a perfect definition. The sub-basic opens of this topology are then of this form, omega inverse of S, where S is an open subset of the scalars, and the small omega is a big omega. And I'll write in this situation V prime for the continuous dual. So V prime is a set of functions from V to K, which are both linear and continuous. And by assumption, capital omega is in V prime, by assumption, by construction, I should say. An interesting question is, can we describe in more detail which maps are in this V prime? Okay, in order to do this, we have to understand the topology a bit better. What is this sigma V omega topology? There is a basic lemma that says the basic opens in this topology around the origin are of this form. So the basic opens are given by a finite number of linear functionals together with the real number, and they are those vectors whose norm is below R. The norm, by the way, is taken in the scalars here. So it's a R norm on the scene. This is completely standard to prove. What you then get is that a function, there's a typo here. So this omega should be this F. So a function is weakly continuous. So weakly means in relation to this weak topology that I define. If and only if there is a bound, and there are finitely many of these linear functionals in capital omega, such that the bound of omega on each V is below V times this union of these things. It follows rather directly from this characterization. But again, this will be useful quickly. Recall we have this double dual map from V to V double star given in this way. Now the image of this map, DDV in V double star, gives you a collection of functionals, but one level higher up. And it defines the topology on V star is equal to weak star. So you go just one higher level up, one additional star in defining this topology. Typically one writes this instead of the more formal where I had the omega previously. And the sub-basic opens are now of this form. The set of omegas such that omega V is in an open S. Or given V and S. Okay, theorem, we can now prove the first step of the results I wanted to prove in the beginning. The double dual map gives a surjection from the continuous dual of the algebraic dual. That is, for each weakly continuous function from V star to K, there is an element in V such that this rho is actually dd of V. Here's the proof. We assume this rho is weakly continuous. By the lemma I just described, it can be described as being below a bound B of a finite join of things which are in the set that generate the weak star topology. So there are finitely many elements Vi which do this. Now if I have this bound property, then it's easy to see that the kernel of all these double dual maps is contained in the kernel of rho. Indeed, if an omega is sent to 0 by all these things, then this norm is 0. So then also rho of this omega must be 0. So you're in the kernel of rho. And remember now this lemma that I started from, this inclusion property of the kernels gives me this linear combination. So rho can now be described as a linear combination of this form, But since the double dual map is linear, I can take these inside, and I can simply write rho as the double dual of these things. Okay, so this gives me, at a very general level already, a form of representation result, but only a surjectivity. It's not good enough. To get better results, we have to move on to vector spaces with a norm. We have to assume some more structure. What is a vector space with a norm? Well, a vector space on which you have a function going to the reals satisfying these three standard properties. A linear map between two of those spaces is called bounded if there is a bound, a supremum, and an S, the real number such that the norm of f of v is below s times the norm of v, and this must hold for all vectors v in capital V. And I'll write n vect of k for the category of such spaces, so the objects are vector spaces, but the norm and the maps are such bounded maps. On such a function between norm vector spaces, the operator norm is defined as the infimum of all the upper bounds that you have for such a function. And this itself is perfectly behaved norm again, so the whole set of bounded functions is then itself again a norm vector space. And in this space you have this very useful property that the norm of f of v is below the norm of f times the norm of v. Good. I'll use the following notation, which I already mentioned in the beginning. I'll write v sharp for the dual of not only linear but also bounded maps. I'll write a ball around the origin as v sub r. V sub less than r is the set of vectors with norm below r. And you can combine these. For instance, this set is the set of linear functionals whose norm is below 1, whose operator norm is below 1. That's useful. Then there are a bunch of useful results for these normed vector spaces, which I'll go through, but the proofs are not quite, not very trivial. You need Hahn-Banach-style extension theorems to prove this. So if I have a linear subspace of a normed vector space, and I have a linear function on it to the reals, I'll do this here for the reals. It's more complicated for the complex numbers, and I only need it for the reals. But if the norm of this omega is below the norm of x for each x in S, then this omega can be extended to the whole space in such a way that the norm of this extension is below 1. This is a very useful property. It relies on the axiom of choice, as you can probably imagine how to set this up. If I have an arbitrary vector v, then I can find a linear functional with norm at most 1, such that omega of v is precisely the norm of v. It's also a useful property. I can also separate vectors. If two vectors in the norm space are different, then there is a linear functional with norm at most 1, which separates these kind of functions, typically Hahn-Banach-style results. And next, for each closed subspace and each vector not in the closed subspace, there is actually a linear functional such that omega is 0 in the closed subspace and 1 in the other. Again, these are separation results which resemble a bit the Hausdorff properties, the T properties. But you describe it now in terms of functions, actually separating these things. Why are these results useful? Well, we can apply them to the double dual map that we're interested in all the time. First of all, this double dual restricts from the stars to the hashes. Why is the norm, the operator norm of the double dual of V below the norm of V? Well, this is just writing out the definition. The norm here of this is the norm of this. This is the definition of the double dual. And because this omega is assumed to be a bounded function, it satisfies this inequality. And I can change this multiplication so it gets the appropriate form and says that V is then a bound, an upper bound, defining that this double D of V is indeed a bounded function. And again, on these bounded functions, I can get a weak star topology by using the image of this double dual map. Now we're getting somewhere. Now we can do some more substantial results. The ball of the R ball of linear functionals is a compact Hausdorff space in the weak star topology. This is a very, very fundamental result that you will probably also use for C-star algebras, but it can already be proved for normed vector spaces at a much more elementary level. And the double dual map is in isometry, so it preserves the norm of the vectors that it operates on. And as a result of this, it's an injective function. Every isometry is an injective function. It's a very easy result. And this is already useful because it shows that we can map V into the double dual in an injective manner. How do you prove the first point? Well, the key step is that this space of linear functionals with norm at most R can be mapped into this big space. This is a product. What I mean here is the interval. So if omega is a linear functional with norm at most R, that means for each vector V, the outcome is in this interval. If I take the product over all these intervals, each such interval is bounded and closed, thus it's compact. If I take the product over all these compact spaces by Tikhonov's theorem, this is again a compact space. And it's not very difficult to describe this as a closed subset of this compact space, hence it must be compact itself. Okay, and the isometry part here is not very difficult. So we already had this inequality. The other follows because in a previous lemma we already saw that if you, for each vector you can find a linear functional such that omega of this vector is precisely the norm of this vector. That gives you an equality here. Okay, so I can now state this duality result for norm vector spaces. That is, for each weakly continuous functional from the bounded dual to the scalars, there is a unique vector such that it comes from this double dual map. And this will in the end be a crucial result that I will need for Kadison duality later on. So please take a mental picture of this because I will have to use it later on. The existence we already know from the ordinary vector space case, and the uniqueness now follows because this double dual is an isometry and has an injection. So we get an isomorphism here. Well, this basically concludes what I wanted to tell today, but I want to finish briefly by giving you a definition of norms, complete norm spaces, because I will use that later on, and I've been using it already implicitly. A vector space which is complete in its norm is a space in which each Cauchy limit has each Cauchy sequence has a limit, like in ordinary metric space. Such spaces are called Banach spaces. We can form a category of Banach spaces. It's a subcategory of these normed vector spaces. And there is a left adjoint to the inclusion of Banach spaces in normed vector spaces. Ordinary completion construction by taking equivalence classes of Cauchy sequences works in this setting. You can define a norm on them in an appropriate way, and you remain within the in this setting, and that gives you a left adjoint, so there's a minimum of way going back. And is ample time for questions. I'll stop here for today. Thanks. You want to share this? You want to share this? There you? Yeah.
Yeah, well, yes. Any questions? Goodbye.
Yes.
The separation property for convex compact counter spaces.
Yeah.
For compact counter spaces, you have heuristics on which says you can distinguish closed sets by pointing into the unit interval. How much stronger is it to be able to distinguish points?
Yeah, Robert has been looking into that. There's an intricate construction which proves this, but the construction is very, very indirect. I've been pushing Robert for a long time already to give a direct proof of this, but I haven't. This hasn't worked yet. Yeah. Maybe you want to comment on this?
Well, yes, it's separating points implies that you can separate, so for convex sets, once you can separate points, you can separate closed sets, or closed convex sets anyway. Whereas for spaces, it's false.
So what's your feeling? How much larger of a class are we talking about?
What do you mean by how much? So
Separated implies unison basically.
yeah, so for convex sets and affine maps, the separating points is equally as good. Once you can separate points, you can separate closed convex subsets. Whereas for topological spaces and continuous maps, there are wacky spaces where you can separate the points but can't separate closed sets. But none of the normal ones work like that. So
Does that
normal
answer
in the normal sense as well.
And you're aware of how you embed those things then in locally convex spaces if you have this separation property?
I think so.
Okay, very good. Then I don't need to know.
Another question? I have a quick question. So this is this summarization that you're doing, as you described initially. Do you see this having some application in some other area, or this is just for the purposes of organising this material in this way? What's your ultimate motivation for?
Using it as a basis for a logical language for reasoning about quantum systems, for expressing and reasoning about quantum systems. Yeah.
So can you explain why you think it's particularly suited for?
Yeah, I will go into that over the weekend. Yeah. So please be patient.
Difficult, isn't it? Okay, are there any more questions for Bart? Okay, thanks.